Okay, it's Mr. E here, and I'm making a special video for Connor. So shout out to him that um, inspired this particular video. It's on the polynomial remainder theorem, and it was prompted by a question that came up in one of our SAT review courses. Um, so I'll show you the question at the end, but first I just wanted to review the polynomial remainder theorem itself. I was just going to review what the theorem says. I'm going to do a quick proof, and then we'll jump into the problem. Okay, so um, you know, the more you do in terms of how you approach a particular problem, the more you know about the topic that underlies the reason for that problem, the more likely it is that you're going to be able to bring back some information that is going to help you to solve these problems both correctly as well as quickly. So here we go. So here's the polynomial remainder theorem. So what it says is that if you have a polynomial, let's call it p of x, p of x. So it's any kind of polynomial. And you know what the form of a polynomial is, something like, a x to the n plus b x to the n minus 1 plus c x to the n minus 2 plus dot 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 all the way down to some constant, right? So for example, let's do 3x to the fourth plus 2x to the second plus 7. That's a polynomial because it's in this form, and here is 4. N minus 2, so this term is not there. N minus 2 term is 2, and the constant is z. So it's in descending order. We say that this polynomial is in standard form because it is in descending order. It is a polynomial of degree 4, right? And so that's an example of a polynomial. And then what the polynomial remainder theorem states is that if you take that polynomial, whatever it is, like this, and you divide it by x minus a, right? You get another polynomial, right? So for example, you could divide this polynomial here, right? So you could divide 3x. Let me make that a little cleaner. This is a 3. Right? You could divide that by, let's say a is 3. And so we're going to divide it by x minus 3. So the a here is 3. This is the polynomial, this is your p of x. And we're going to divide this. So let's do that long division really fast. So we have x minus 3. We'll do a little review of polynomial division. You could use synthetic division if you wanted to do it quickly, right? So we have 3x to the fourth. And then, I don't know if you remember what we sometimes will make it easier if you fill in the missing degrees, right? So 4, 3, so there's 0 times x to the third plus 2x to the second plus 0x to the 1 plus 7, right? Okay, we're going to divide that. X minus goes into that 3 times, right? 3x to the third times. That's why I'm putting it in the x to the third column. Right? If you want the degree column is like the hundreds place in long division. And then I'm going to multiply back, and I get 3x to the fourth minus 9x to the third, right? And I'm going to subtract that, which means I'm going to add the inverse. And so I get 9x to the third, and then I bring down the 2x squared. Then I put that in there, it goes in plus 9x squared times, and then this becomes 9x to the third. And that's 9 times 3 is 27, so this is minus 27x to the second, right? And then we're going to subtract that again, which means we add the opposite, and we get now 29x to the second. And then we bring down the 0x, that's going to go in 29x times plus 29x. This is going to be 29 to let's bring this up a little bit. 29x squared. This was plus 0x to the 1, and that's going to be minus 9 times 29 is, well, it's 3 times 30 minus 3 is 90. 90 minus 3 is 87, so it should be 87. Minus 87x. Let's just check that. 29 times 3, that's 27. 2 times that, sure enough, it's 87. I got that by multiplying 3 times 30 and then subtracting out 3, right? And then that's going to be plus 87x, and then we're going to have plus 87, and 87x plus 7. We're going to get 87 times 3. Now I have to really multiply that out. Times 3 is 21, 24, 26. I'm not sure that all this is really worth it, but I've kind of gone down this path. Anyway, you can see what I'm getting at, and there's going to be a remainder. Did I do that correctly? 21, 24, 26, I think so. So it's plus 87x minus 261, and that's going to be plus 261, and that's going to give me 268 is going to be my remainder, right? So anyway, you get some kind of polynomial when you finish that. So I'm going to call this polynomial the quotient. So I'm going to call that q of x, right? So I got p of x divided by x minus a is equal to this whole polynomial, right? C of x, no, what do I call it? Q of x, right? Q of x. And there's a remainder, though, of 268, right? And so what we normally do with that remainder is we divide it by the denominator, the divisor, right? So this is going to be q of x plus 268 divided by x minus 3, right? Which is really x minus a. So I'm going to call this the remainder. Okay, and to leave it all generic, because I've left this generic, that's p of x. It doesn't state what p of x is. This is x minus a. It doesn't state what a is. This is the quotient. It doesn't state what it is. And this is the remainder, but it has to be true that when you take p of x divided by x minus a, you get the quotient plus the remainder, whatever it is, divided by x minus a, right? And if I multiply that whole thing through by x minus a, right, this whole thing, both sides, I'm going to get p of x on the left side, right? I'm now multiplying x minus a to get rid of these denominators. I'm going to multiply the left and the right sides of the equation by x minus a, and that's going to give me this new equation that states that p of x is equal to q of x times x minus a. I guess I'm doing the proof first, plus the remainder, right? So that's a true statement also, because I had this true statement, and then all I did was multiply both sides by x minus a. So what that's really stating is the following. Look what happens when I find p of a. Now let's calculate p of a. So I put p of a in here, and that's whatever this polynomial is calculated at a, right? Over here I get this quotient, q of x. I still don't know what that is, but I get, this is going to be a minus a, and this is going to be remainder, right? And a minus a is 0, so this whole thing drops out. So this states that, and this basically states the remainder theorem, that if you evaluate a polynomial at a, which has been divided by x minus a, that the answer to that polynomial evaluated at a will be equal to the remainder. Will be equal to the remainder. Okay, and that's what the polynomial remainder theorem states. So let's go back to that for a second. So the polynomial remainder theorem states that if you have a polynomial, p of x, and you divide it by x minus a, then it will be true. It will imply that p of a is equal to the remainder of this operation. So you find what p of x divided by x minus a is, you find the remainder, and that remainder, r, will be equal to p of a. Okay, so let's make it real. Let's see, well, dare we go back to this other one and actually calculate it? So for this problem here, it's really saying that p, remember that p was this polynomial, that p of 3, so here we were using a equal to 3. So let's calculate what p of 3 is. So if I'm going to add this in, 3x to the 4th, so it was 3x to the 4th, so the polynomial x was equal to 3x to the 4th plus, what was it? It was 2x squared plus 7 plus 2x squared plus 7. And if we calculate p of 3, that's going to be 3 times 3 to the 4th plus 2 times 9 plus 7. And I'm going to calculate what 3 to the 4th is. That's 9 times 9, which is 81, right? 3 times 81 plus 18 plus 7. And 3 times 81 is 243. I probably should have calculated something that had some easier numbers. But we have 243 plus 18 plus 7. That's going to be 250, 268. And lo and behold, look what our remainder was before. I think it was 268. Was it not? Let's go here. Ah, look at that, 268. So we did all that math and it was correct. That's amazing. So what we've stated again is that if you take a polynomial, p of x divided by x minus a, you find what the remainder is, that was 268, then 268 has to be the value of p of a. P of a. That's all that states. Okay? So now let's go to this particular problem that Connor and I were working on the other day. So we had this problem, and now you don't have to memorize all these formulas. You don't have to do any of this stuff, but you do have to remember what the polynomial remainder theorem states. Okay? And I'm going to show you how now to use that in this particular problem that we're going to work on. Okay? So here is the problem that I brought up the other day. This came from an actual prior College Board practice test exam. It was an exam number 1, which was actually taken off the College Board site a couple of years ago when they went to the new format, which was only online. So look at this problem. It says for a polynomial p of x, the value of p of 3 is minus 2. Which of the following must be true about p of x? Okay, so what is this kind of, let's look at this information first and see how it relates to the polynomial remainder theorem. So remember that 3, what you're putting in here, this is the a, right? So we know that the polynomial p of x, we don't know what the hell that is, but we do know that we have divided it by x minus a, and x minus a is the same as x minus 3, right? Because a is 3 here. And we further know that p of 3, right? We do know that p of 3 is equal to minus 2. So that means that when you took p of x, right, and you divided it by x minus 3, you got some other polynomial, remember the quotient polynomial, but the remainder, q of x, but the remainder was minus 2. So that's all that the polynomial thing states, right? And lo and behold, that's exactly what this says. It says the remainder, look at number D, the remainder when p of x, here it is right here, is divided by x minus 3, is minus 2, and that's all it states. Now, these ones, you can eliminate these right away, because look at this. In this case, the a would be 5, and this states nothing about 5 in any case. This is when a is 2, and this says nothing about 2. It has a 3 here, and it has a minus 2 there. This has an a of minus 2. So that's sort of, this is the closest thing that has anything to do with the given information, because the a here is minus 2, and here's a minus 2. But that, so, you know, that could be the problem. But what it would state is that if that's the a, if a is minus 2, then x plus 2 is a factor. It's not a factor because the remainder would be 0, and therefore this should be 0. If x plus 2 is a factor of p of x, then the remainder would have to be 0. But anyway, you can see that this last one is definitely the right answer, directly from the polynomial remainder theorem. Okay, so I hope that helps. And I think we really killed it there. Again, you don't have to know the proof, but if you have the proof in the back of your mind, or if you have the remainder theorem in the back of your mind, you're going to be able to kind of not quantify, but kind of restate the problem in terms of the polynomial remainder theorem. That's all I did here, right? I looked at this. I knew that this had to do with the polynomial remainder theorem because I saw these x minus 2 forms, x minus 5, x plus 2. So that gave me the clue that this had to do with the polynomial remainder theorem. Okay. We also looked at the answers. The answer has this remainder here. So again, another clue that this is about the polynomial remainder theorem. I looked at the information that was provided to me. I saw that a would have to be 3 for the polynomial remainder theorem, so I filled that in. I knew that the value of p of x was minus 2, so I knew that that was going to be the remainder, right? That minus 2 was going to be the remainder, and that fit my question D. So you wouldn't spend any time on all the things that we talked about today. You would just identify that the problem is the polynomial remainder theorem, identify the givens, and see if you can kind of translate that into the information that is in the polynomial remainder theorem. Okay, hope that helps. Again, a shout out to Connor on this, and good luck. Ciao.